so we already kind of talked about this. This one is 7-4. We already talked a little bit about this in class. So we're going to first just match up some stuff just to show what it looks like, to give you an idea of some of these graphs. And then we're going to go into it a little bit farther. And then again, we'll practice some more tomorrow in class. So just bear with it, get through it as much as you can. So right here, guys, you notice this one, nothing cancels out. If you look, this one, nothing cancels out. This one right here, you have x squared over x. This has an x and an x in common. Therefore, one of these x's can go away, but if one of them goes away, you still have one up top. So really, it makes it x over 1 or just x. So that is the graph we're going to be looking for. This graph is going to turn to y equals x, which is a linear, but it's going to have a hole. There is going to be a hole at x equals 0. Because that's what makes this denominator 0 right here. This guy totally cancels out and turns into 1, but again, we're going to be looking for a hole at what makes the denominator 0? 2. So let's go through and kind of look at some of these graphs. So let's do the first ones that we know. We know this one right here is going to move things to the right 3. So my horizontal asymptote, or my vertical asymptote, is going to go to the right 3. So if I look through these, right 3, right 3, right here. Looks like this thing is moved right 3, 1, 2. Oh, that's only moved 2. Is it 3? Oh, what am I saying 3 for? My fault. 2. It's supposed to be moved 2. So it moved 2. This right here would go with the first one. So that function was 1 over, so this one would be 1 over x minus 2. Alright, we're going to kind of move on to these guys that we talked about that are holes. So if I look for this one, I'm going to be looking for the equation y equals x. Y equals x is a linear equation. Think about it, it's y equals 1 over 1x plus 0. The reason I'm writing it like that is there's my slope, there's my y-intercept. So I'm looking for a line that has a 0 as the y-intercept. So 0, 0 is going to be on there. And it's going to have a slope of 1, 1. But if I look, there's a hole at 0. So actually, it will not have this intersection. There will be a hole there. There will be a hole at that spot. So I go through, and this is a line. And yes, it has a hole, but it's not the one I'm looking for. If I go right here, you can see it has a hole here. I go up 1 over 1, up 1 over 1, up 1 over 1. This would be the equation to that graph. All right, let's go back up here. Got a lot. Let's get rid of some of this stuff. Again, if I was graphing this one, this would be the equation y equals 1, and I'd have a hole at 2. So what happens with this, that equation is y equals 1. That is a horizontal line where y equals 1, right here. Okay? So y equals 1. But the problem is there's a hole at 1. Right here, this is the correct line, but the hole is in the wrong spot. So that's not my graph. So I keep looking for a graph that's similar to that. And when I go, I have one right here, and it's the same. That's y equals 1, but I've got a hole at where x is 2 because that situation that we had up top. This guy right here, when I cancel these out, that becomes a 1, so y equals 1 again, but now my hole is at 0, and if I look, that's this guy right here. All right, let's try this one. If I cancel this out, this becomes x squared up top over 1. And so when I do that, I'm going to be just graphing y equals x squared. So it's going to be a parabola, but I have a hole in my parabola at x equaling 0. X equaling 0. So I'm going to look for a parabola, put my hole at 0. There's my parabola right there, and I have a hole at 0. Hopefully you kind of get that understanding. Alright, so we're going to skip through, and that's kind of the gist of it so far. So this idea of these holes, where they're happening, is called removable discontinued. It's right here. And we talked about this in class today. It's where they cancel out. So right here, you can cancel. So this has, so if I wanted to know what graph this is, it's actually the graph y equals x. And the way I got that is because I have x times x up top over x times x. That's really what x cubed means, and this is really what x squared means. Well, every time you have an x, and remember, all this is multiplication in between. This cancels out, this cancels out. You're left with an x on top. X over 1 is just x. So I'm going to graph this line, but because I have a denominator where what would make it 0 is if my x was 0, so I have a hole at 0. So I'm going to graph this linear equation just like normal. I'm going to graph it. My slope is rise over run, 1 over 1. My y-intercept is 0. So I go to plot that, and I go, wait, that's where my hole is happening. So I put a hole there, and then up 1, over 1. Up 1, over 1. And then I draw my line, kind of skip that spot, and there we go. That's what it should look like with that hole being right there. All right. So I skip to this next section, which is page 574, and right here, I'm doing the teacher guide. Right here, what happens is you see this x squared and you see these x squared. These guys cancel out, so all you're really graphing is y equals 2 is all you have to graph. But you have to remember, there is removable discontinuity at 0, because if you put 0 in, that makes it a denominator. So that's where my hole occurs. So you can see the graph looks normal, and then all of a sudden they get to 0, and they put this little hole there, and it hops over it, and it keeps continuing on. Look at this graph. When you cancel things out, this equals, well, what happens when you have x squared up top? Remember, it's like x times x over x times x times x. So what happens is these cancel out, and you're left with 1 on top. Make sure you leave that 1 up there. So this is really like graphing 1 over x, which is what we've been doing this whole chapter. So that's why it looks like this. Yes, you have a horizontal asymptote. Yes, you have a horizontal asymptote. I'm sorry. You have a vertical asymptote, like we've been doing, and this graph looks like this. And there should be a hole at x. There should be a hole at x equals 0. But the thing is, there's an asymptote at x equals 0. So we don't have to worry about this hole because the asymptote overrides it. Now, if I go back to some of these ones up here, guys, I should have mentioned this. You still use your rules. When I go to graph these, like if I was going to graph this one, there is no horizontal asymptote. We do need to remember our horizontal asymptote. When I went to graph this one, there's no horizontal asymptote because the top is bigger than the bottom. So don't forget those rules that we've done so far. I'll try to bring those up a little bit more. So I'm going to go through just, if you graph these, this shape should look familiar here because when you cancel this out, you end up with x cubed. Again, the top power is bigger than the bottom power because this is a third, this is no power, so there's going to be no horizontal asymptote. There is no vertical asymptote because it's 1, but there is a hole because I had that removable discontinuity at 0. So again, they graph this thing, and it should look familiar. It looks like a cubic function. That's because we graph it like a cubic function because that's what's left over when I cancel everything out. But there is that hole that I need to remember. This right here is going to look like -1 over x squared. And so that's why this graph looks like that. And there is a hole at x equals 0, but there's an asymptote that overrides the hole. So sometimes you can have a hole and you can have an asymptote, but sometimes the the asymptote overrides the hole. All right, now this is where we were talking about a lot of stuff is going to happen. Before we can decide whether there's a hole, before we can decide any of that, we've got to factor this guy. So remember, I can factor this because it's just this is just a 1, no special cases here. So I've got double bubble right away, 2 numbers that multiply to a 6, but different signs, so they're going to subtract to a 1, and it's a positive 1, so the bigger number is positive. So I've got different signs, plus and minus, x, and I've got a positive 3 and a negative 2, and then that's over x minus 2, and what do I know is going to happen with these guys? That's going to cancel out. So I'm going to graph the line y equals, or f of x equals, x plus 3. I'm going to graph that line, but I'm going to have a hole. There's going to be a hole at x equaling 2. So I'm going to graph this sucker just like normal. So if I went to graph this guy, you would graph it, and my y-intercept is 3. So if you notice, they plotted 3 on there. They used the slope, up 1, over 1, up 1. But when they went here, they said this is where x equals 2. So they put a hole there. If you notice, everything else, though, is filled in. So it's basically, guys, just a review of everything that we've done. You can see any of the graphs that we've done, cubics, quadratics, you can see linear, but some of them might have holes because something cancels out in the numerator and the denominator. And again, when I canceled out, my numerator was bigger than my denominator, so there was no horizontal asymptotes. All right, this person right here, you can see this thumbs down is huge. You got to watch this book, guys. You got to make sure when they give you the thumbs down, that means that she did something wrong. What she did was she thought that she could cancel this term out with this term and this term out with this term. And we talked about that today in class a little bit. She cannot cancel those terms because between them is plus signs. The only way that she would be able to cancel them as if this was written as something like this, x squared times the quantity 4x plus 3. Whatever is in the top has to be exactly in the bottom. Now, if she had this, where you have the multiplication between these two terms, so you've got this term and this term, and these guys can cancel each other out because that's multiplication, and these were in parentheses together. So she would be able to do that. But the way she did it, with the way it's written right here, she cannot cancel that out. So you might want to read through what they're saying on some of these things. All right. So these are going to be excellent examples to look through. I'll talk through a couple of them, but obviously you can tell the first thing that they're doing, I'm going to be in problem A. I'm talking you through it. All they're doing is they factored this guy. They said, hey, there's a common factor of 2. When they factored out of 2, which they skipped this step, this is what you got to be careful of, they get 2x squared minus 4. Now when you read it like that, hopefully you see the difference of squares that popped out, and that's how they got to here. Once they did that, they can cancel these out to a 1. In the book they say you can't cancel out. So you understand the concept is they're canceling out to 1, then you're good. And then what they did after is you want to distribute this 2 back to everything so you can see it written as a 2x plus 4, and there is a hole at x can't equal 2. Again, my top is bigger than my bottom, so there's no horizontal asymptote. There's only a hole at 2, so if I was graphing this, I'd go up 4, 1, 2, 3, 4. That would be my y-intercept. Up 2, over 1. That would be that guy, and I would keep going until x equals 2. You want to make sure you put that hole in your graph. So I'm going to keep going until I get to x equals 2, so I got to go up 2, and over 1, and when I go over 1, that's where my hole is occurring. And then the rest I can just draw a line through and a line through, but I want to make sure that I actually get that in the right spot for my hole. All right, this guy right here, again, the first thing they did, this is difference of squares. This has a common factor of 3y, so they factor out a 3y. When you pull out a 3y, what times 3y gets you to 3yx? You're missing just x. What times 3y gets you to 3y? You're just missing the minus 1 because it's just multiplying by itself. Then when they do that, that's where they got this from. They can cancel out these two terms. And then you're left with 3y over x plus 1. And then you're listing right here. They're listing even though that, so x can't be positive 1 or negative 1. And one of them is a whole. So this right here, this would be a whole, whereas this one would be a asymptote. So one of those is a whole, one of those is an asymptote. So those, when they say list any restrictions on the domain, they mean list anything that x cannot be. So I'm going to just kind of pop this up here. You can hopefully look through the rest of these answers. What you might want to do is pause the video before this, try some of them on your own, see if you can do these factors, and these are the answers for them. If you have any questions, we can go over them. We're going to go over some more examples like this in class, but definitely you might want to try this before you look at it. Try it on your own, and then do some. If you look right here, they factored this guy by grouping. So this one right here, I'll do some of the work for it. It's put in common. If I do that, I'm left with a, what do these guys have in common? They have an x in common, and I'm left with x squared minus 5. What do these guys have in common? Well, I need it to become a positive, so I need to factor out a negative, and then I'm left with x plus 5. That's what I wanted. So then I'm left with, oh, I'm sorry, because my big fat pen. These guys have an x squared in common. That's my fault. So then I'm left with, and this screwed up too. Since I factored out a negative, it became x minus 5. Remember, I told you you can cheat because you know this bubble should be the same. So that's how I'm checking this and seeing where I made my mistakes. So then I get x minus 5 times the quantity x squared minus 1. And again, this is difference of squares. And that's why they broke it up into x minus 5 times the quantity x plus 1, x minus 1. So that's just examples of how they factored it. And then they can cancel out the things they have in common. So the x minus 1s, they kind of turn into 1s, as the book calls them. I call it canceling out, but it just means they cancel to 1s. These reduce to a 1, I guess is what they want you to say. And then you got to make sure you list everything. So what was in the denominator? It couldn't be 1 or 5. That's just listing those restrictions. All right, with this guy, all they want you to do is determine whether the graph is a vertical asymptote, removable, neither or both. So right here, when you can cancel this out, there's a that's removable discontinuity at 2. That's what this one is. And then there's still, this turns into 1 over x. So there's still a vertical asymptote at where x equals 0, because if you put 0, it would make that 0, or it would make it denominator 0, which is a vertical asymptote. All right, this guy, nothing can cancel out. No, you cannot cancel out the x's. That is incorrect. You cannot cancel those out. So this is only a vertical asymptote. You can cancel out the 5s, but there's no way for that 5. That's not a whole. That's not an asymptote. You end up with 1 over x plus 2. The only thing that could, this 5 that was there, there's no way that I could plug a number into this 5 because it's a constant. So me canceling out doesn't change anything. It's still just a vertical asymptote problem. Here, what they did is they factored this bottom. When they factored this bottom, nothing canceled out. Nothing canceled out here, so they just still had vertical asymptotes. No holes appeared. I hope you guys are understanding this. As we go through tomorrow's lesson, hopefully this will drive this one of the final lessons home. And I think that should be good enough to get us through. All right, make sure you do some practice on this, and I will see you tomorrow in class.